Hello everyone, welcome to this video. In this series of videos, you will learn about performing structural analysis of wind turbine blade that is using FEA in ABAQUS CAE. Alright, so I have divided this video into three parts based on your request that if I can divide my videos into smaller chunks. So what I have done is you can do a lot of test and analysis for a structural design of your blade or whether you're doing integrity assessment, but if you look at the standards like DNV-GL standard or IEC 61400 standard, they tell you clearly that you have to do a lot of tests if you are proposing a new blade or material, right? So you need to do a lot of tests at different levels like coupon test and then also component level test. But it also says sometimes the quantity of these tests or number of these tests go up to 3000 to 10,000 as well. But it clearly says also that you can use FE analysis to reduce the number of tests required, and the idea of this video is to show you some ways of doing it. So in the first part what I will show you is I will show you how to perform free vibration analysis to get the natural frequencies of the blade without any loading, and then I will show you how to apply an edgewise load on the blade and then perform a free vibration analysis to see the effect of edgewise preloading on the blade, and then I will compare it with the blade's result without any loading. Okay, then the second part I will show you how to apply flapwise loading on the blade and perform a test onto it, and then do a free vibration analysis to see if there is any impact of flapwise loading on the natural frequencies or mode of vibrations of the blade. And finally, which is another important real life problem, is the impact of an object, which could be a bird impact as well. So if something strikes your blade, what sort of damages can occur in your blade? So how to simulate that process again will be discussed in part 3 of this video. By doing this video or by going through these videos, you will learn about static simulations, how to perform free vibration analysis, which is used for natural frequency analysis, multi-step simulations because we have preloading due to edge or flapwise loading, so we need to first load the structure, which is step 1, which is a general step, and then we need to use the free vibration analysis step to find out the natural frequencies of the system. So we will learn about multi-step simulations. You will also learn about FRP composite modeling, whether it's a deformation or failure, and how to define the orientation on different plies as well. And also you at the end, for the bird impact case or object impact case, you will learn about explicit dynamic analysis. I have simplified the problem since I have taken this geometry from GraphCAD. So what I have done is I have removed all the internal structures to reduce the simulation time. So there is no structural support available inside the blade. If you are familiar with the blade architecture or cross section, you can have a lot of structural features inside, such as stiffeners and spars and all those kind of things. I have removed those, and that's why all our results will be very low, because we only have kind of a composite skin, which is more for the aerodynamic performance rather than the structural performance, right? But the process will remain the same if you have multiple components. You just need to tie them together or bond them together, as we have done in my other videos. All right, so let's jump into the first part then. Okay, let's move into the details of how to model a typical wind turbine blade and find out the natural frequency modes without any loading, and then I will show you how you can apply the edgewise load and then also perform the free vibration analysis to get the natural frequencies of the modes. And we will then try to compare and see what is the effect of preloading, which could be edgewise load or flapwise load. So in the first part I will show you the edgewise load. Okay, so this is the model as you see on the screen. I took this model from GraphCAD. So what I do is I just import the component as I normally do, and I can import many different formats. So in this case I had an STP file, so I actually imported that, and once you import that you will have this kind of part which is there. I use the default options if you really want to do it, so you can go and grab this one or any other 3D model from that. The next thing is obviously to apply the properties. In this case I have defined the density and also the elastic properties, which are in 3 directions as I did for the other composite cases. So if you are not sure about how to define the material properties of a composite material, then please have a look at the video which is shown on the top here. Okay, so that's how I define the material properties. Then I don't have to create sections as I do for other material definitions. You see there are no sections here, but I need to define the plies. So for that I need to go for this option where I say composite layup manager, and then I create this ply. When I press the create button, I will get this kind of window here. And as you can see, in this case I am using 12 plies. Again, these are taken from somewhere, so these are all assumed things. The thickness of each ply is 0.25 and I have 13 plies. So I start with positive 45, minus 45, 90, then 90, then minus 45, 45, and so on until the last one, which is this one. So in this way I have 12 plies. All right, so these are the plies I have defined. Anything else? I had the material definition, so I'm associating it with that. For the orientation, this is the angles I have prescribed, and they control. You can see when I click on it, you can see the orientation for each ply. So there are 12 plies in one shell element here. All right, so this is how I have defined the orientation and plies with properties to account for the orientation effect of material properties. Then I go to the assembly and I assemble the part. So what you have to do, you have to go to the instance, click on this and press OK, and your part will be in your assembly module. Then I go to the step, and since I'm doing a free vibration analysis, so what I have done is I can press create, and I can select frequency analysis. So I need to select the, instead of general, I will select linear perturbations step procedure, and then I will select frequency because I need to extract the frequency, natural frequencies of the system. And once you open that thing, then you will have these different types of solvers. Again, if you can look at my other videos on free vibration analysis, there is some discussion on that, and there are some other very nice videos on YouTube as well on these solvers. So I'm going to use a Lunchos type solver. I am going to ask it to give me 12 modes, and rest is all default. So you can see I haven't changed anything at all. The only thing is, remember, you have to remember that these frequency analysis uses a symmetric solver, matrix storage and solver. So if you have unsymmetry in the loading, for example due to contact, friction, whatever, then it cannot accommodate for that. All right, so now that's done. So I have defined the step this way, and then I go to the interaction. So what I have done is I have no contact here because it's just one part here. But if you have multiple blades and you have a whole rotor blade, then you might have to define some contact properties as well. So there is no interaction property here. However, to apply the displacements or fix this end of my rotor blade with the hub, I have coupled it by creating a reference point. So how to create a reference point? You can go to tools, press reference point, and then you can select any point here. So you see I have selected this reference point here. So your reference point is there, and then you have to couple it. So you can create constraint, and then you select coupling option, and when you click continue, then you will get this window here. So you have to first select the control point, which is this reference point, and then the surface. So I have selected the whole surface of this hub, this thing. I mean, I assume that this whole thing is fixed with the hub with the help of boards or whatever. Okay, and I'm coupling all the kinematic constraints. So all the displacements and rotations are coupled with this reference point. So whatever I do with this reference point will be applied to the whole of this surface here. Okay, so that's what I have done here. And now what I'm going to do, I'm going to fix this point here. So I'm going to fix my rotor blade with the so-called virtual hub. And for that, what I have done is basically I have, see, you have fixed all the degrees of freedom in this along this direction. And in addition to this, I don't have any additional loading right now, so I'm not preloading my structure. And I will show you in the next case how you can apply, let's say, edgewise loading or flapwise loading, and then do the same analysis with multiple steps. Okay, so this is all I have done here. So there is no loading. As you see, there is only one boundary condition, which is this one, to fix one end of the blade. Then I go to the mesh, and I have used, as you can see, I have first select the part, and then you can see I have, so I have went through an easy process of meshing, and I haven't paid too much attention on how to mesh it. So I use a try mesh for these shell elements, but you can try others as well if you want and if you have time for that. So that's what I have done. Again, mesh is not optimized, so that's again for that you can look at my other tutorials how to optimize mesh in basic geometries. So this is what I have done. If you look at the element type, just to show you that, so the element type in this case is a standard quadratic elements I'm using, which are recommended, and shell elements. Okay, so that's what I have done here for triangular elements. Nothing else is required. So once I go there, I create a job, I name the job, and I save it, and then I submit. So once I have this job, I just submit it, and you can see it's completed. So instead of submitting again, I am just finishing it, so you can see how it works. So it just, I needed only one, it just solves all in one step basically, or one increment, because it's a frequency analysis, and there was no issue with that. So let's look at the results now, how different natural frequency modes look like and what could be their values. Okay, so let's look at the results now. For this, I have removed the mesh, which you can bring back if you are really interested. All exterior edges will bring the mesh back, but I prefer to have it like this to look at it better way. And then I can press this, and you can see if I get to the start, so this is my base state after frequency analysis, and then this is my first mode with a frequency value given to me as cycles per seconds, because we are working with millimeters and seconds. And you can see it's just the bending mode in mainly flapwise direction, as you see, with some edgewise rotations as well. So it's very much like that. So I hope this makes sense. Then you look at the next mode of vibration, and that is this kind of mode, which is more unrealistic in my opinion, but you can see, and its frequency is around that as well. So it's because these frequency modes are very close to each other, because we don't have any structural support, and it's more aerodynamic shape which is there with some composites. So if we have internal stiffeners and spars and all those kind of things, then these values might be very different. All right, and then you can play around with that, and you can see different modes here, frequency modes and so on. The only thing now, so just remember that the first mode was bending mode, which was mainly flapwise sort of loading with some edgewise bending as well, and its value was 0.11704 cycles per second. Now what I do, I say, okay, now I have a preload. So what I did was I did a test where I applied some kind of load on my structure, and then let's go back to the model, and then let's say I started with the edgewise loading. Okay, so I go to the edgewise loading now. So my part remains the same, right? So my properties remain the same, as you can see, same mass density, same elastic properties, and then same number of plies and everything. So I don't need to change anything in this. What I can do is, in reality, I can just copy the previous model which I had here with this, and then I include some loadings and also add some steps to make it make it like a preloaded wind turbine blade under frequency analysis. Okay, so that's what I have done here. So everything else is the same. If you go to the step here, you will see some differences. So now I have a general step, and if you look at the general step now, it's 1 second with an incrementation of 0.01 with a maximum of 0.1 increment size, right? And it is going to run for total time of 1 second. And I have done this because I want to apply an edgewise load onto it. So edgewise load will be something acting on the edge of the thing, and it will try to bend it in along z-axis in this case, or about z-axis in this case. Okay, so that's what I have done, while the second step is the same as frequency step as I did before. And just solver, I'm asking for 12 frequency modes, or natural frequency modes. All right, so that's what I did in simple terms. So now I go to the interactions. Interaction is again the same. You can see there are no contexts defined, which we don't require. It's one part, but for interaction I created a reference point as I did before. It can be, if you're copying the same part, it should still be there, and I just coupled them together with kinematic constraints. Okay, so that's what I have done here. Then I go to the loads, and loads is the main thing. Now you see there are no loads here in reality. Okay, I haven't applied a force or pressure here. In reality, you will have a wind pressure I didn't have those values right now, so I didn't apply that, but if you have some values, you can try those. And what you have to do in reality is you need to take your sample or material or your structure to the lab and apply under the wind tunnel loading. You apply different types of wind loads and try to measure the deflection, and then you can apply those deflection on your blade as an edge load. Or you can use some other type of softwares, like if you have pressure sensors installed on your blade, you can also measure those through that to apply those pressures. Or you can also use some softwares like Blade and Fast, which can also give you aerodynamic loads on your blades depending on the profiles and structure. Okay, so in this case I didn't have that, so I went with the easier way, being lazy, you know. So first thing is the fixing of this thing, which is always the same as before. So everything is fixed, then and it's propagated through the last step as well, which is the frequency step. While in the second case I'm applying an edgewise displacement, so it will try to bend about z-axis, not realistically the edge load, but if you know the displacements through the experiments, you can apply displacements as well. So that's what I have done here, and they are applied as a ramp during step 1, which is a general step. So after the step 1, it will be pre-deformed and pre-stressed, and it will go to the frequency analysis, and we want to see if there's any difference or effect of preloading on the natural frequencies of the system. All right, and then we have a nice mesh. Just joking, I'm not good at meshing. And finally I just run the job. So again I go to the job module and I create a job with a name. So in this case I use an edgewise FVA. This means I have an edgewise load, and then I do free vibration analysis. Okay, I run it and I get this completed. So you can monitor and you can see it went through okay, and then at the last step it finished after 15 increments, and then the second step was the frequency step after the loading. So let's look at the results and see what we find. If you remember that previous case without any loading was 0.11 something. All right, so this is the model. Now I will rotate if I can. Now what I do is I deform, and what you see now is there is slight change due to the preloading. So if I look at my preloading step, so this is my initial step with nothing. Then I apply edgewise loading, and you see I have edgewise displacements plotted here. I can also plot stresses because this is a static general step, so it can give you stresses as well, and you can see a lot of stresses here. So again, you can design based as per your design criteria. You can see if you're reaching to the critical stress times some factor of safety or not. I will keep the displacements again because next step is the frequency step, and it only gives you displacements as an output. So this is the first mode. This is the base state, right? And this is the first mode, and you can see it is 0.119 as compared to 0.1107 or something. I remember. So if I go back to the free vibration analysis thing, plot the base state. So first one was 0.117, while in this case my first one is 0.119. So there is an effect of the loading, and that is captured here. Again, as I told you, there are no structural features here, so these are not realistic for this blade, but because it's all this, we only have the skin based on the composites, and we don't have any internal support structures inside the blades. All right, so this is what we have done, and you can see other modes as well, and you can compare with the preloaded and the loaded one as well. If you want to compare both of them, you can create a viewport, and then you can arrange them vertically, for example. And in this one I will bring the free vibration analysis without any loads. Okay, and so this is the first mode as you see here, while and this one, so this is the first mode here, and this one is the first mode there. So modes are pretty similar, but you can see the values are slightly changed because of the preloading. Again, if you have severe preloading or more stresses, strength based components inside the structure, then it will definitely have different distribution. So this is how you do it for an edgewise loading. In this case, as I told you, I applied only displacement, but you can apply pressures or loading if you have some realistic values. But for that, again, you will have to have some internal structural supports, which could be stiffeners and spars and other stuff to support that kind of pressure. In this case, it was just a skin, and I just wanted to show that for the demonstration purposes. So this is how you do it for your free vibration analysis for a wind turbine blades, and without and with loading. So in this case we applied an edgewise loading. So I hope you got some idea on that.